Today I will discuss module 5 of unit 4, alternating current electricity or AC. Before going ahead, we should discuss and we should have an idea of current electricity which we have done in previous module. This module will cover AC circuit, component in AC circuits, comparison of circuit component in AC circuit with that if used in DC circuit, reactance mathematically. We also discuss here pure R, pure L, pure C, that is resistance, inductance and capacitance, as well as we will discuss phasor representation, resistor. We also discuss here the phasor representation, numericals, etc. Our objective of this module are to discuss about alternating current circuit, to differentiate different component in AC circuit, to explain electrical circuit using pure resistor, inductor and capacitor, to know role of those element in AC and DC as well, to represent R, L and C geometrically. We also discuss and draw AC waves and its variation, explanation of formula and its relationship. We will also represent phasors and AC distribution in pure R, L and C, and we also practice some numerical and problem solving based on current and electricity. As we know, AC electricity allows for the use of resistor, capacitor and inductor within an electrical or electronic circuit. These devices can affect the way of alternating current passes through a circuit in a network. They are only effective with AC electricity. So, let us start with considering simple AC circuit that contain only one circuit element, say resistor, inductor or a capacitor is connected to a AC source. So, since we know that we have a circuit here AC source where resistance is connected in series. So, according to Kirchhoff law, as we have done earlier, the second loop rule says sigma E is equal to 0, that is to the given purely resistive circuit we have V naught sin omega t minus I r is equal to 0, that is I is equal to V naught sin omega t divided by R, where I r is equal to V naught sin omega t. Here R is constant, which is resistance, that is V naught divided by R is equal to I naught. Here I naught is current amplitude or peak value. That is what Ohm's law, which for the resistor is applicable for the both AC and DC voltage. At any instant of time, Ohm's law is valid for such a circuit resistors which are in series or in parallel, or it may be grouped together into a single equivalent resistance, or in order to apply Ohm's law or analyzing in the circuit. Here we can see the phasor or the variation of I and V with respect to time. So, we have this time dependence of current and voltage across the resistor, where what we can see here the value of I and V just start from the 0 and it is with respect to time. The behavior of I r and V r can also be represented with the phasor diagram. The phasor is a rotating vector having the following properties, that is number 1, length, and the length correspond to the amplitude. Angular speed, the vector rotates counterclockwise with the angular speed omega. Projection, the projection of the vector along the vertical axis correspond to the value of alternating quantity at time t. So, here we can see from the graph what we have seen. It is evident that both V and I reaches to 0 or minimum and maximum. These values are at same time. Clearly, the voltage and the current are in phase with each other. That is, the average value of current over one period carries as, and it can be written as I r t, which is equal to 1 by t integral 0 to t I naught sin omega t is equal to I naught divided by t 0 to t sin 2 pi t divided by t dt, that will equal to 0. That is because of omega is equal to 2 pi by t, and which is f is equal to 1 by t. So, this average value vanishes because of sin omega t for a complete cycle of 1 by t 0 to t sin omega t dt is equal to 0. The fact that the average current is 0, however, does not mean that the average power consumed in is 0, and that is there is no dissipation of electrical energy. Thus, there is joule heating and dissipation of electrical energy with an AC passes through a resistor. The power dissipated in a resistor is P R at certain time interval t is equal to V R I R or I square T R. From the average over one period is obtained as power P A at time t is equal to I square R, that is equal to 1 by 2 I square R, which is equal to I square R, that is I V m, that is V square divided by R. Also the value of I square R t does not vanish. It means we can see here I square t 1 by t 0 to t I square t dt is equal to 1 upon t 0 to t I square sin square omega t dt is equal to I square 1 by t 0 to t sin square 2 pi by t dt, that is equal to 1 by 2 I square. From here we can define the root mean square current as, from here we can define the root mean square or RMS current as I RMS is equal to under root I square is equal to I divided by under root 2. Here we will show through the circuit diagram how current and voltage varies at a constant resistance. So, we have this is a battery, here we are showing through the diagram. Suppose I change the value of voltage. So, how this red button is showing how current and voltage are varying. Even we can see it through the graph. If I draw the graph, we can see here how current and voltage are varying at a constant resistance. Here we have a value how we calculated R as V upon I. Suppose we have a resistance of 470 ohm. So, at that point we have a value of current is here around, you can see the value we can calculate from this point, it is 20.6 milliampere, and at that time the voltage is around 9.67 volt. Now, we will discuss at the same time how the inductor behaves when the source of AC applied in the circuit. Say we have a AC source V is equal to V naught sin omega t, and we have an inductor L which is in series connected to the AC source. So, a purely inductive circuit as shown, the inductive circuit correspond to infinite capacitance C as infinity and 0 resistance, that means we do not have any resistance in the circuit. Applying the modified Kirchhoff rule for inductor, we have V t minus V L is equal to V t minus L d I by dt is equal to 0. That is, this implies d I L divided by dt is equal to V t divided by L, that is equal to V L divided by L sin omega t. Here we have used the value of I is equal to I naught sin omega t, as we can say V L naught is equal to V naught, that is peak value of voltage. Integrating over the above equation, we can say that we have I L t is equal to integral of d I, that is equal to V divided by L integral of sin omega t dt, that will equal to, if we integrate it, it will comes out V divided by omega L cos omega t, since we know integral of sin omega t dt is cos omega t, that is equal to V divided by omega L sin omega t minus pi by 2. So, we can say also here the amplitude of the current through the inductor is I L is equal to V L divided by omega L, which is equal to V L divided by X L, where X L is the reactance and which is equal to omega L, and this is called inductive reactance, and its SI unit is ohm as of resistance. Just like we can say we measure resistance, we will measure inductance here. However, unlike resistance, XL depends on angular frequency omega. The inductive reactance vanishes as omega approaches to 0. That means, when angular frequency is approaching towards 0, the phase constant is phi is equal to plus pi by 2. Here the current and voltage plots and the corresponding phasor diagram for purely inductive circuit is given below. We can see here it. The variation of voltage and current, when there is inductor in the circuit, there is a phase difference, means there is a phase difference of pi by 2 between voltage and current, that is the phase is of plus 90 degree. That means the time dependence of IL and Vt across the inductor shows phasor diagram for the inductive circuit is showing that the variation of voltage and current, that is current lags voltage by pi by 2 in purely inductive circuit. So, we can say that the inductor when used in a circuit, when it is connected to a source of AC, it shows that current and voltage has the phase difference of pi by 2. Now, we will discuss, suppose an capacitor is connected to AC voltage or AC source. So, how it looks like, you see this diagram. In a purely capacitive case, both resistance R and inductance, that is 0. Here we apply Kirchhoff voltage rule as Vt minus Vc is equal to Vt minus Q divided by C is equal to 0. This gives Vt is equal to Cv is equal to Cvt, that is equal to Cv sin omega t. Why we using here that peak voltage and induced voltage as V is equal to V naught sin omega t. So, we will write it as Cv sin omega t, where Vc is equal to peak voltage. On the other hand, we can say the current is Ic is equal to dq by dt is equal to omega Cv cos omega t, that is omega Cv sin omega t plus pi by 2. The above equation indicate that the maximum value of current is Ic is equal to omega Cv, that is equal to V divided by Xc, where Xc is equal to 1 by omega c, which is called capacitance reactance. It is also have the same unit as resistance has, it is measured in ohm, that is the effective resistance for a purely capacitive circuit. We can note here the Xc is inversely proportional to both C and omega, where C is capacitance of the capacitor in the circuit and omega is the angular frequency, and it diverges as when omega approaches to 0. The phase constant is given as phi is equal to minus pi by 2. It is just reverse of inductor, where phi was is equal to plus pi by 2. Then the frequency f is equal to 1 upon 2 pi under root L C, where L is measured in Henry and C is measured in farad. The current and voltage plot the corresponding phasor diagram for a purely capacitive circuit is given as below. We can see here the variation of current and voltage with a certain interval of time, there is a phase difference of minus pi by 2. That means, when voltage is starting from the 0, that time current start from pi by 2 or 90 degree. So, we notice that at t is equal to 0, the voltage across the capacitor is 0, while the current in the circuit is at maximum. In fact, Ic reaches its maximum before by 1/4 of the cycle, as Vt is written as phi is equal to pi by 2. Thus, we say that the current leads the voltage by pi by 2 in a circuit when capacitor is used. So, here we can summarize the capacitance and inductance are inherent properties of an element just like resistance. Their reactive effects are not exhibited under constant direct current, but only when the conditions in the circuit changes. Thus, the reactance differ with the rate of change and the constant only for the circuit under alternating current of constant frequency. In case of vector analysis of electric circuit, resistance is the real part of the complex impedance, while reactance is the imaginary part. Both share the same SI unit, that is ohm. An ideal resistor has 0 reactance, while ideal inductors and capacitor consist entirely of reactance, that is XL is equal to omega L, which is equal to 2 pi FL, where F is the frequency and L is the inductance. At the same time, Xc is equal to minus 1 upon omega c, which is equal to minus 1 divided by 2 pi Fc. Now, we can share some part of problem solving here, what we have done previous in the chapter or here the same what we have discussed today. So, we can start with this. Can you imagine what about the automobile batteries usually supply the voltage? Can you guess? Say like 240 volt, 120 volt, 12 volt or 9 volt. You can just guess. I can repeat it like this. Suppose we are using a battery in a car or in a bike. So, what supposed to be the supply of the voltage? It will be around 240 volt, 120 volt, 12 volt or 9 volt, right. Okay. So, it is about 12 volts. Next we can share one more here. Can you guess which component has positive and negative side? We are using say a potentiometer, fuse or a resistor and a battery. Quick, you have to answer. So, it is battery, right. Now, we have one more. For a pure inductive circuit, what you can imagine? I am giving some option to you. The inductive circuit consumes some power on average, does not take power at all from the line or takes power from the line during some part of the cycle and then returns back to its during the other part of the cycle. So, what will be the answer? The answer will be it takes power from the line during the some part of the cycle and then return back during the next cycle. Here one numerical for you, just answer what supposed to be the frequency of a sine wave like a country we are living, say India. So, it will be, okay, guess, just calculate, it is 20 hertz, 30 hertz or 40 hertz or 50 hertz. Good, it is 50 hertz. One more question for you. Capacitive reactance is more when the capacitance is less and frequency supply is less. Capacitance is less and frequency is more. Capacitance is more and frequency is less, or capacitance is more and frequency of supply is more. The answer is capacitance is less and frequency supply is less, means both must be less. Okay, one more question. Why power in a circuit is 0, in which current voltage are 90 degree or out of phase? Okay, just you can do it. What we have done earlier, when we were using the inductor or capacitor with the AC source, that time we have shown in phasor also. Say if current and voltage are 90 degree out of phase, then the power P will be 0. The reason is that we know that power in AC circuit, power is equal to VI cos phi. If angle between current and voltage is 90 degree, then power is equal to V I cos 90, cos 90 is 0, then the power will be 0 in case of pure inductive circuit. One more question for you, why power is 0 in case of pure capacitive circuit? Since we know that in a pure capacitive circuit, current leading by 90 degree from the voltage, or in other words we can say voltage is lagging 90 degree from the current, or the phase difference between current and voltage is 90 degree. So, if current and voltage are at 90 degree out of phase, then the power will be 0. That is, the reason is heat, means heat is produced. We know that power in AC circuit as P is equal to V I cos phi. We will put the value of phi here 90 degree, then power is V I cos 90. Again the same thing will happen, cos 90 is 0. So, if you put cos phi 90 is 0, then the power will be 0. The same thing will happen in pure capacitive circuit. So, in brief, what we have learned today, we have done AC circuits, component in AC circuit, comparison of circuit component in different circuit, reactance mathematically we calculated, we have done what will happen when we will use pure resistor, pure inductor, pure capacitor in AC source. We also done phasor representation graph for each. So, we have finished this module, and in next module we will discuss about the R, C, L, and we will combine them like R C, L C when the circuit connected to the AC source.